good afternoon, good evening, wherever you are. And what I'd like to do is go over a few ground rules, a few things first, and then we'll get right into the content. I'd like to highlight some key aspects of this channel and tools for you to explore while you watch. In the Downloads tab, you should find some materials and web links to find documents related to our content today. And you will find a Questions tab, which you can ask questions at any point throughout the presentation. And we'll try to handle all the questions at the end of the various presentations. I hope you enjoy today's presentation, and please get back to us. At the end of the webinar, I will also have some links for you in some of the slide sets. As I mentioned, my name is Michael Schulman, and I will be your host today and a moderator. So why are we here? Well, I'd like to start with this example. So you get home from work at the end of a day and you want a nice cold bottle of wine, but nothing is cold in your refrigerator. So you have two choices here. You can put the wine in a bucket of ice water, or you could put it in your freezer. Which one do you think will chill the wine quicker? Well, the answer is, and I don't have the exact numbers of minutes or seconds, is the bucket of ice water. So kind of why is this? Well, liquids and water have a tremendous amount of more cooling capacity than air. You can see from these numbers, the cooling capacity, the thermal conductivity, and the transport energy is much greater with liquid than with air. So we're going to be using this in the data center, and we're going to explain how this can help you cool your data center and save energy and save money. So what's happening in the data center today? Well, the latest generation of CPUs are running at 280 watts and will probably go higher in the future. When you put two of those in a server with multiple GPUs running at 500 watts or more, you've got a big cooling problem. You're talking literally having to remove kilowatts of heat from a single server. Traditionally, it's been an air cooling problem. Let's force as much air over the server chips and the GPUs as we can, send it out the back, and then let the air conditioning in the data center actually chill the air. Okay, but this is going to run into some problems soon, and we're going to talk more about this. It's becoming harder and harder to remove the heat just from air cooling. So liquid has the ability to carry this away. Carry the heat away. So in summary, before we get into the details, why is liquid cooling important? Well, switching from air conditioning to more effective liquid cooling can reduce operating expenses by up to or more than 40%. Liquid cooling, it dramatically improves the PUE of the data centers, and we have some numbers about that, for high performance, high powered CPUs and GPUs. This liquid cooling is not if you're just going to have one or two servers. When you have racks and racks of servers and need to take away many, many kilowatts of heat, this is an option that people should start to consider. And this reduces costs and environmental impact, not just power, but then the power generation, the fossil fuel emissions and things like that. So what we're going to do today is have a discussion among Mark Ng, who is our product manager here at SuperMicro, who specializes in rack level design and has architected and worked with many of SuperMicro's largest installations. We will also be joined by Brian Wu, who is a senior thermal engineering manager who's in charge of our liquid cooling servers. And we're excited to have Dave Martinez here from Sandia National Labs, whose title is Engineering Project Manager for Infrastructure Computing, that's a mouthful, and has worked extensively in the design and implementation of liquid cooling for large systems. So first, welcome Dave, Mark, and Brian. So first we're going to go to Brian. And SuperMicro has a range of servers that are used in many industries and many workloads. Can you talk about which servers we see most frequently and why certain servers are being used for or need liquid cooling? Okay, go ahead, Brian.
Okay, thank you. And thank you, Michael. As current, the power consumption trend in the market, we can see the processor power from 10 years ago to currently power already rise 100%. Original processor power is around 130 watt only, but in current market, we already see the CPU power already over 270 to 280, no matter Intel or AMD. And we can see in the future, we can see the CPU power will continue going high. And not only CPU, also for the GPU. For the GPU, and we can see the current market is very hot for AI, deep learning, so a lot of applications, they use GPU to do the calculation. So for GPU power, same as CPU. We can see right now the GPU power is already from 300 watt up to 400 to 500. And in the future, not too far, we can see the GPU power will over 500 watt, maybe up to 600, 700, we don't know. So for all of those CPU or GPU, if their power is going high, absolutely we have to use the liquid cooling because there is a limitation for air cooling cooling solution. Because for traditional air cooling, we use heat sink, but the air, the heat exchange rate is much lower than use liquid. So we can see in the future, not too far. At this moment, we already start a liquid cooling solution in the market. So Michael, can you go to next slide? Okay, thank you. So for liquid cooling, we can see there are a lot of benefits. The first one, as I say, it can save a lot of power from processor. Okay, no matter GPU or CPU. If the power over 500 watt, absolutely we have to use the liquid cooling to achieve lower temperature for the processor. This is what we have to do. Otherwise, the semiconductor cannot carry so much high power for them. So we have to use very high efficiency cooling solution. So that's the first one. Is why we use liquid cooling. The second one is we can see a lot of power saving if we use if we use liquid cooling. So the first one is we can see the power savings from our system because if we use liquid cooling solution, we can reduce our fan power. This is the first one. But the major power saving is from data center point of view, because if we use liquid cooling, we can reduce a lot of equipment from AC air condition. Right? And the second one is we can reduce a lot the power saving, and we can also reduce a lot of facility like a PDU or some component to saving a lot of power. So this is why we can see the power saving from liquid cooling. And the power saving means the cost saving because we don't need to use so much power from city. So we can have a lot of cost saving for the liquid cooling solution. Yeah. So, okay. Michael, yeah. So here in SuperMicro, we do have some liquid cooling system to support this market. The first one is the GPU server. Right now, this is from NVIDIA technology. The SS74 GPU from NVIDIA already going to 400 to 500. And for 500 watt GPU, absolutely we have to use liquid cooling. So no matter the market need a 4 GPU or 8 GPU, this is what we do, what we prepare for this market. This is a GPU system. Yeah, and next one. Yeah, and this slide is show our CPU liquid cooling solution in our CPU system. No matter the 2U phonom or our blade system or generic server, we all have the liquid cooling solution ready for the CPU, no matter use Intel or AMD CPU. Yeah, thank you, Michael.
Okay, thank you. Okay, next we're gonna, hey Mark, how are you doing?
Hey, Michael, how are you?
Okay, well, as I mentioned, Mark runs the SuperMicro data center rack integration team. And a few years ago, Mark, we started to work with customers that has significant cooling requirements. So let's start from the process. When you get notified of a customer that might need liquid cooling, what are some questions that you actually ask?
Thanks for having me, Michael. There are a few factors. So we first look at the server or the workload requirements. So with that, being said, that means we'll have to look into what processor or the quantity of node that is needed to satisfy that performance that the customer is looking for. Next thing would be the network topology. So the network topology plays a very important role because the customer always wants to maximize the use of the ports. And the number of ports don't usually come as we want to. So they come either in a few flavors, whether it's 48 or 60 or 32. And that means that on the layout, we'll have to spec in a multiple of that per rack layout. And that affects how the entire cluster is then laid out on the floor. After that, then we will need to discuss the facility power and the cooling support. So most of the data center have already pre-built-in cooling equipment and power equipment. And we need to understand their environment setup. And that usually means that for every square foot, the data center already has previously spec'd in, okay, I'm gonna have this cooling capacity for this amount of real estate. And that plays a also very important role on how to sort of retrofit or fit in the design or the system that the customer wants.
Okay, great. Thank you very much, Mark. We'll come back to you with some more questions about specific type of liquid cooling options. So let me go to Dave Martinez, who I mentioned works at Sandia National Labs. He's well known in the HPC community as a specialist in design and implementation of liquid cool solutions for high density. Dave, thanks for joining us.
Thank you very much.
Okay, so in the national labs, you're kind of looking with the large clusters that you guys use. You're looking down the road 2 to 5 years. What do you see as some of the cooling requirements that everyone's going to have to be concerned with, 2 to 5 years down the road?
Oh, yes. Basically, everything we do is a big percentage of liquid cooling, whether it's 30 to 60% liquid cooled into the computer racks themselves right now, as we're dealing with densities from 30 to 70 to 100 kW per rack already. So on the HPC side, we're really facing that issues now, and we just completed a new data center that's 14,000 square feet, and it has 14 megawatts entering it. So that can tell you, kind of tell the tape of exactly where we're going to go and what we're going to expecting for liquid cooling. So,
okay.
Yeah.
Okay, great. So much higher power and higher density as well.
Yes.
For the CPU manufacturers.
Yes.
Means everyone's going to have to think about liquid cooling. So since you guys do this so far in advance, can you briefly tell me how these large installations that you're familiar with, when do you start the planning process for whether you're going to need liquid cooling and what types you might use?
Yeah, right. It's delivery of services, what your expectations are from your customers or who you're delivering the services to. If you could look at the roadmap for what type of computers you're using now and look 5 years down the road, you could get a really good idea of what you're going to have to deliver as far as services, and that tells you exactly where you need to start and be for liquid cooling. If you haven't started looking at liquid cooling, I think you're a little bit behind right now, and you need to probably start looking at your infrastructure and see how you can start adapting, at least starting with some cooling doors to get familiar with liquid cooling and how it works, and the enhancement it does for your data center, along with the capabilities it gives you on the economization side for saving energy.
Okay, yeah, you got to start planning well ahead for some of this.
Yes, sir.
Okay, I'm going to go back to Brian here. We're going to see Brian's picture. So Brian, if a salesperson or customer comes to you and wants to use liquid cooling in a certain type of server, how do you figure out if that's going to work, and how to then engineer these servers to handle liquid cooling? How would you do that?
Okay. Yeah, so usually if we got a demand from a sales or customer, first one, we will figure out which system is much better to fulfill a customer demand. And so far, what we got most requirement from customer is for high density computing demand, and no matter they use the CPU computing or GPU computing. So in current experience, what we meet is if they need a CPU computing, we will propose our existing solution that can use the blade. We do have super blade. They can achieve 8 AU and 20 node. Or use our twin system, they can achieve 2U4 node. Those systems can fulfill high density CPU computing. Or if the customer need a GPU computing, of course, we do have 4 GPU system from NVIDIA Redstone or 8 GPU system from NVIDIA Delta. And both of them, as currently we see, already fulfill over 80% to 90% of marketing demand. But if customer, they do have a lot of special demand for some special system, absolutely we can do the customize based on our building block solution to figure out which system they need and then build a liquid cooling solution in the which system.
Yeah. Okay, yeah, so, specific servers lend themselves better to liquid cooling based on the workloads. And, we'd work closely with the customer to determine if we need to do additional engineering work, right?
Yes, correct.
Okay, great, yeah. Okay, so let me go back to Mark. Since Mark works with many of our customers in determining what types of liquid cooling is needed. So Mark, why don't you walk us through this general slide, and then we'll dig deeper into the different types of liquid cooling. Go ahead, Mark.
This slide talks about is a quick, I guess, direct-to-chip explanation. So it needs 3 basic elements on this RackCDU system setup. What happens is you have cold plates built into the servers or the nodes. And each of these cold plates have an internal loop that you will connect to the CDM, the coolant distribution manifold, which then connects to a heat exchanger, which is the RackCDUs, with the first loop that gets, again, reject the heat to the facility, either water or it could be coolant or any type of heat rejection equipment.
Okay, so that's just a general overview of kind of the pieces that are needed. So let's dig a little bit deeper into the direct-to-chip cooling with this diagram, kind of relating it to what you just saw, or what you just talked about.
Right. This is a diagram how the setup is. So basically, you have a cluster on your data center. Let's say you could have a RackCDU per rack basis, or you can have a full-size CDU. Then you'll collect that heat from the nodes, and it will go through the heat exchanger. The heat exchangers then will utilize the facility liquid to expel that heat outside of the building, outside of the data center.
Okay, great. So now, here's what we call immersion cooling. Can you explain more about immersion cooling, which scares a lot of people?
Right. This seems a bit more complicated. However, in laying terms, it's basically having your server or your node submerged into liquid dielectric solution that doesn't conduct any, and you have all the components in the system releasing or basically having contact with that liquid, so that the temperature all around the server is kept at a certain range of temperature, and you will not have any hot spot, or it's more efficient.
Right. And if some of our attendees go to our liquid cooling website, we actually have a video on there that shows literally putting these servers into the immersion tank, and it's really interesting to watch, and it's very efficient. So everyone should take a look at that. Okay, then the other way, it's not exactly liquid cooling, but we kind of clump it together, is rear door heat exchangers, which I know that Dave had mentioned. So Mark, can you explain a little bit more about how this works?
The rear door exchangers, I will give a very similar example. It functions like a car radiator. So it consists of a coil and is cooled by a combination of having liquids and fans on it.
Okay, and I think, it's pretty, we know a number of our customers have used that, and we'll talk about, that in a moment, but, there's a lot of ways to do this, but it's really putting a door on the back of your rack, right?
That is correct.
Okay.
So the idea of the rear door exchanger is that we want the coil located where the heat source is, as close as possible. That way you get it more efficiently, you get more air through the coil, although you can have the door basically hang anywhere on the data center, it will still do their job. But again, as a more efficient way is to put it as close as possible to the source of heat.
Yeah, as close as possible. Okay, let me go back to Dave now. So Dave, you've worked with a lot of vendors, and based on what Mark talked about, how do you determine which type of liquid cooling or even rear door heat exchanger should be used in an environment? Do you try to understand kind of the workloads and how busy the CPUs will be?
Well, absolutely. So we take a look at we take a holistic view because we do a lot of parallel computing. So basically, a computer system works as several different computers work as one. So you're computing and creating a lot of heat, and the memory as well is a little more dense, and the supporting electronic components and power supplies. So that all couples into what type of liquid cooling you want, what type of solution, and as you move toward the higher densities, you want exactly where the heat source is, mostly on the chipset, and then some of the memory and some of the other electrical components. So the immersion would be arguably the best, but if you did a combination of takeaway on the chipset and then a rear door, then you're getting pretty close to room neutral once you're done.
Right. So after you've implemented or designing this type of liquid cooling, whatever type, how do you measure the effectiveness? Do you run simulations, or do you actually compare to an older generation, or what you did for it? How do you measure this?
Oh yeah, perfectly. That's a good question. So we look at we use a Splunk, and then we look into the power of the CPU that it's drawing and the capacity of which it's fully loaded at. And so basically we watch if it's a 98% utilization and our liquid cooling is delivering what it should be. We watch for throttling back of the CPUs or the memory itself. So we know we're effective if we can run 98 to 100% utilization and we see no throttling back. So we gauge that based on that, and we elevate our temperatures until we reach the optimum curve, mostly in the system itself, but also with the facility system. So we're actually saving energy as well.
Okay, that's really cool. The throttling back is a really interesting topic. Let me go back to Brian briefly. So Brian, how hard is it to engineer a new server to use liquid cooling technologies? I mean, is it, we know how to do it, but is it a fairly quick process, or does it take a long time?
Yes, usually if we got the new generation the technology from CPU or GPU, usually we do have maybe a couple months to do the development job. So we work with the vendor very closely, and we work with the GPU or CPU supplier, no matter Intel, NVIDIA, or AMD, very close, so we can get their new technology or their new processor in the very early beginning. So when we got the trend or their spec from their processor or GPU, we will start to prepare the liquid cooling solution. So usually before customer have demand, usually we all have the solution ready. So but the challenge is right now we can say is the marketing supply chain lead time. So we still hope we can get a demand earlier because the manufacturer maybe still need a couple of weeks to prepare. Yeah.
Okay, so I mean, for everyone out there, look at the pictures of liquid cooling servers, and you'll actually see how the plumbing is done, which is really, really cool. Okay, Brian, continuing with you, and just one more question here. I know you've done these simulations on, kind of comparing liquid cooling to air cooling. Can you just quickly go through this chart and show us how someone could figure out how much the cost savings would be?
Okay, this chart is just a very brief example. We just roughly calculate based on our GPU server. And this one is we compare for our GPU server, use the air cooling and liquid cooling to do the comparison and to see what is the cost benefit if we use liquid cooling. So the first one we can see, the first one is from system level, we can save in a lot of power. When use liquid cooling is from system fan, we can reduce fan speed. Because the major power already cooled by liquid, so we don't need the fan speed rise too high to cool the major component like a CPU or GPU. So we can save in a lot of fan power. And the second one is, as I say, from facility side, we also can save in a lot of power because when use liquid cooling, right now we do have some experience in East Asia. The PUE we can achieve to around 1.1 for the data center. For the generic air cooling data center, the PUE may be around 1.4 to 1.5, and it may be higher. So based on this saving, they're saving a lot of power. So we just use the very generic power cost from this is the USA average cost, 12 cents per kilowatt hour. So based on the total power cost saving, we can saving maybe over $40,000 per rack per year. Right?
Okay, yeah, I mean, yeah, that's real cost savings by implementing liquid cooling. Absolutely. And this isn't even for that large of an installation that you have your example for. Yeah. Okay. Let me go to Mark. So Mark, we've had some large scale successes with liquid cooling. Can you go through a couple of these, starting with Lawrence Livermore's Ruby system?
Yeah, I'll give you a quick introduction. So this one was deployed at Lawrence Livermore. Code name, they call it Ruby cluster. It was installed last year, and it ranked number 79 on the top 500 list on November 2020. So a quick overview about the architecture was designed with the Twin Pro series and Intel's OmniPath networking. And it was about a little bit over 1,500 nodes. And it had 84,000 cores and 290,000 gigs of memory. So the peak performance was about 5.9 petaflops.
Yeah.
And it was built with the in-rack CDU liquid cooling, direct-to-chip liquid cooling. Next
Okay,
slide.
yeah, and something maybe you want to mention is that we have the ability to put all this together in our factory here, right?
Right. So we have built our factory at scale, and we are able to build almost full-scale clusters within our facilities. We assemble the nodes, we test the nodes, we test the liquid cooling, and we test the entire cluster as a single unit. And that's how we built this Ruby in San Jose headquarters.
Right. And then we have another installation in Japan. Can you talk a little bit more about Squid?
Right. Can you go to the next slide? Thanks.
Yeah, I'm on the Squid slide.
Okay. So Squid is a fancy name. Let me see if I remember what it stands for. It stands for Supercomputing for Quest to Unsolved Interdisciplinary Data Science. It was installed last quarter in Osaka University. And is also around 1,500 nodes. They used 42 GPU nodes and a few vector nodes. This cluster was designed with HDR, and it had a, I guess, theoretical 16.5 petaflops of performance. It was also installed using direct-to-chip in-rack CDU liquid cooling technology.
Okay, yeah, it's a great installation, and we have a press release there or a case study for people who want to learn more about this. Okay, back to Dave with kind of near the end here. What do you see in terms, of will liquid cooling solve everything, or are we going to have to look further and further of other ways to cool really hot systems? Dave? Are you on mute?
Yes, no, I'm here. I'm
Okay.
sorry.
Okay.
The future of HPC is carved out for most high-performance facilities. As we know, more speed will equate to more densities and power draws, etc. So basically, the liquid cooling right now should suffice, and however you want to deploy that is what will give you the edge. So as you move toward a more immersion type liquid cooling, if you're not there yet or getting close to it, then I think you're ahead of the game. And then that will enable you to use warmer water, liquid cooling, save energy. And to the points made earlier on the OPEX, you basically will save operating costs, pump energy versus fan energy, along with space, because fans take up a lot of space in the data center, in and around the data center, where pumps take a small amount of space. So it's the way of the future. It's just a matter of what you want to do after you receive the liquid cooling. If you want to use it for reheating, whether you want to heat a building up or use it for low grade heat, or if you want to brew your own beer, you could preheat the water going into the brewery. Yeah.
Yeah, we know of some installations in one of the Nordic countries, where they're actually shipping extra heat to the city to then heat homes. That's pretty cool.
Absolutely, yeah. NREL is involved in the design of NREL, and they heat about 80% of their campus with the waste heat out of their data center.
Right, okay. So we're going to continue to see more heat. We got to get rid of it.
Yes, sir. Yes, sir.
Okay, Mark, so you had mentioned 2 large installations which are on this chart. Can you talk briefly about some of the other ones that we've done recently with, I think these are all rear. Well, go ahead. Why don't you go start with the NASA one?
Right. NASA cluster was a smaller cluster. It was 560 nodes. They liked our Fat Twin series, and it was also designed with the Intel Owning Path networking. Because of some, I would say, mechanicals limitations on the data center, I believe they used the rear door exchanger. So they loved that, they liked the lights, and they were very customizable to their data center. The other one, which is worth mentioning, is the IMS. The IMS is the Institute of Molecular Science in Japan. I believe this one was the largest deployment we had for rear door exchanger. They also have data center limitations. They want to maximize their real estate, so they wanted a lot more compute on the racks, and they didn't have enough space. So the rear door exchangers really fit that need. And the others are Rutgers University, which is also using the rear door exchangers. And I guess the last one would be the previous Osaka one.
Yeah.
That was done also with the first generation of direct liquid cooling.
Right.
They had what do you call that? A lot of cooling towers on their facility, so they wanted to maximize that. And the on-chip cooling was basically connected to those cooling tower, not directly to the chillers. The chillers only went on, I believe, on the month of summer, so they were running pretty efficiently.
Oh, okay. Yeah. So yeah, I mean, and to everyone out there, we work with a whole range of vendors that work with SuperMicro for direct-to-chip, immersion cooling, rear door heat exchangers, and so forth. So, bring us your challenges, and we can find and work with a vendor that supplies the right type of equipment. Okay, so I want to first thank Mark, Dave, and Brian for being here today. We actually got some questions in here, so let me start with the first one. Does the water cooling plumbing consume a PCIe slot? I assume the answer is no, correct, Mark?
That's correct.
Okay. This is in one of the slides, you could see how it's done out there. Do you have any pictures of actual liquid cooled environments? Well, we showed you what we have. I'm going to mention something else where you actually can see it in working when I go to a summary slide. Yes, we will have some of the slideware, or will be able to be downloaded from the BrightTalk site. Otherwise, get in touch with me. And here's one. I'm not sure if this is for Mark or Dave, but this came in. What calculation can be done to find out if you've reached the limits of air cooling? How would you determine if you need to now think about liquid cooling if you're already, if you have air cooling? Dave or Mark, you want to handle that one?
Usually it's KW. You look at your KW per ton and how much air CFM it takes to put in front of the rack to actually cool it. Around 20 to 20 plus kilowatts, you need to start looking at some type of enhancement for your liquid cooling. That's sustained 20 kilowatts a rack.
So or you'd see some throttling, or you would see some CPUs actually fail, correct?
Actually, yeah, and then you'll also, your environment within the data center, so a holistic view of your data center will start heating up. If you were able to measure it with some type of thermal imaging, you would see that you're actually passing some of that hot air into the front of the other racks, etc.
Oh, okay. Yeah, so watch how hot your servers are getting, and that'll be an indication of if you need to look at liquid cooling. Here's one really interesting. Are there trade-offs in adopting liquid cooling, serviceability, reliability of the heat exchangers? Do you have any experience with that, Mark or Dave?
Dave, do you want to speak to that?
No, go ahead. Can you repeat that again?
Okay. Are there trade-offs? So is there serviceability or reliability of the heat exchangers that you have to be concerned with, or are those really they're going to work for a long, long time?
Yeah, so as long as you don't have an open system and you have closed loop systems and you have the right water treatment, you should be fine for many, many years down the road. And periodically just checking your closed loop system's water and sending it off to a Nalco, whoever it may be, just to see where you're at. So you should be fine.
Okay.
Right. So what we've seen is that these systems are built to last at least, a generation. We usually train the customers and we make recommendations according to each different partner. So let's say whether it's a annual visit or annual checkup on those systems, make sure they're working properly. They do not need to be recalibrated, or everything is in order. So in terms of serviceability, yes, you will need to learn this new type of system, how to do the service and the checks and things like that. So
okay,
that's a bit of trade-off. Yes.
Okay, I'm not sure if any of you guys know this, but is there any warranty issues on immersion cooled systems?
Okay, this is Brian.
Yeah.
And right now, we do have some experience with liquid cooling, immersion cooling system. We sell with partner. So far, SuperMicro offer a warranty with the CPU computing node. Yeah. And for the GPU portion, right now still working with a vendor because this is very new industry for AB1. But basically, we do offer a warranty. I don't remember, at least 3 to 5 years for the CPU servers. Yeah, this is what we did in SuperMicro.
Yeah. Okay. Here we have another question. Can we, this probably is for Brian or Mark, can we customize the system with liquid cooling? So I'm not sure what customize, but kind of, once we have a server and, you work with our teams, we will ship it up. I don't know, you want to open it up and customize it on site, right,
yes,
guys?
Yes, this brand, yeah. Usually, we accept the customized system with liquid cooling, depending on the demand. Of course, this is a business, so if it is a high volume, high demand, of course, SuperMicro offer a customized system with liquid cooling. Yeah, because if the volume is not too much, we will suggest customer to based on our building block solution and to use our existing system for liquid cooling demand. I think SuperMicro can offer most of customer demand, based on our solutions. Yes.
Right. We have a whole range of solutions, so we hope we have already done some customization for you in advance. But great question. And the final question before we wrap up, maybe this is for Mark or Brian again. Does SuperMicro produce and sell any special liquid or oil for one-phase liquid cooling systems?
Okay. This brand. So far we work with partner for the liquid cooling solution, and all the coolant, or we say the coolant or liquid, is qualified by the vendors because they do have a lot of experience to use those coolant to prevent some effect with our cooling module. So if there's demand, we can work with a partner to sell those coolant for customer. But we hope that we sell is based on our mark product we deliver to customer.
Yeah. Okay. Great. Okay. So that was lots of questions. Thank you. So what I'm going to do now is, first of all, let me switch this around. I want to thank everyone for joining today. We had a great turnout from what I can tell. Let me now give you some of the more information or where to go. And some of this actually came online yesterday. So what I want to do is, for more information. So the biggest thing is go to our webpage, supermicro.com/liquid-cooling, and I have a little snapshot of it in the upper left. We have a data sheet, we have a white paper, and the image you see at the bottom row in the center, we had a reporter or someone who, not necessarily a reporter, but someone who looks at technology come in here about 3 weeks ago, and he actually tested systems that were air-cooled and that were liquid-cooled. And he wrote a very nice article, complete with photos and videos. This video was uploaded to YouTube yesterday, and as of this morning when I saw it, we already had about 7,000 views. So if you search for SuperMicro liquid cooling, this is from Serve the Home. Take a look at it. It's a great video that explains a lot of what we were talking about. And you actually see these liquid cooling systems. These were live, and I want to thank Brian and Mark for helping with that tour for Patrick Kennedy. So we've gotten a lot of interest in this, and we think moving ahead with all kinds of CPUs and GPUs and whatever XPUs, what's coming next, liquid cooling is going to be a very important part of large-scale, high-performance data centers moving forward. So I want to thank everyone. Thank you, Dave. Thank you, Mark. Thank you, Brian. Please go to the website and tell your colleagues they'll be able to download this from Bright Talk fairly soon. Okay, thank you, everyone, for your time.